Is that correct? Okay. So you remember that just what we talked about compressibility index? Yes, we talked about this one. So under compressibility index, there are two parameters. One is called cast index. The other one is Houghton ratio. So in the industry, you need to use at least one. Either use this one or use the other one. Of course, you can also go for both. Alright? This one is simpler. You just take that density divided by bulk density. Then you look at the limits. Good, poor. That's all. So once you get the ratio between 1.25 to 1.5, then you have to add a Gleiden. Remember just now I told you what's the difference between Gleiden and Newton? Remember? Okay, the next one is compatibility and compressibility. The two terms are slightly different. You read, see whether you can understand. Compressibility refers to ability to decrease in volume under pressure. Compactibility is ability to be compressed into a tablet of specified tensile strength. When you make a tablet, you will say how compact the tablet is. When you want to compress a granules, you will say whether the granules are compressible. Understand? Understand? Because when you study powder, you know certain powders are plastic, certain powders are elastics. I don't know whether you study different classes of powder. So you need to go for plastic powder. So this kind of plastic powder can be easily compressed. The one that is elastic, you compress, you apply a load, a force. But once you remove the load, what happens is, you can go back, right? Because you release. So what will happen? You will get capping. Have you done camera? Not yet, right? Not yet. Oh, okay. So have you studied chipping, capping? Not yet. Alright, never mind. When you study, then you remember what I've said, then you will understand. Okay, the next one is wet durability. Wet durability refers to those particles or powders that are very difficult to be wetted. So for this kind of powder, what you have to do is you have to add surfactants or you add a co-solvent. This co-solvent improves the wetting. So how do we know that the particle is actually fully wetted? I don't know whether we have done this kind of test. Very simple. You just take a drop. This is the surface. So you can compact into a tablet. Let's say you take it into a 16 mm or even bigger. Then take a drop of water. You put on top of the surface. Then you can measure the angle. So this angle refers to the contact angle. The bigger, the worse. Alright? It depends on the value. So value is low, that means easily better. Alright? Because of the shape. You get this shape and you get this shape. You can see the difference, Alright, this is another set of experiment. This is actually using a plate, then you measure the angle, but we hardly go for this. Because this one is easy to be conducted as compared to this. You can also go for this type. Actually, there are many experiments. If you're interested, you can just go to Google, you type in how to measure contact angle. There are plenty of experiments that you can go for. For us, as long as that experiment, which is simple and easy to be conducted, and it serves our purpose, then we will go for it. Alright? So problems associated with variability of powders may be solved. If you come across powder like this, what are you going to do? You can mix with a hydrophilic excipient. Understand what's hydrophobic, right? Hydrophilic is easy. Hydrophilic like water. Hydro is water. So you can go for PVP, HPMC, PEG. These are the common excipients, also common polymers. So a lot of times we go for PVP, or you sometimes also can go for PEG. PEG is more common used in the chewable tablet and lozenges. And PVP very common as a binder. You can also incorporate a surfactant. Remember just what I mentioned to you? Surfactant basically is a surface acting agent, right? Yeah. Okay. So you also use surfactant as emulsifying agent, right? Alright, so you know. Don't worry, I won't ask you this. This is only for your reference. Don't worry about this. You are not sitting for max. Alright. This one, I believe you have done it in the second year. Right? You talk about crystal, you talk about amorphous and crystalline. So I'll go through this quickly. So crystal properties and polymorphism. You know what is crystalline form, right? So basically because of the arrangement, very systematic. Then amorphous, there's no certain form. But amorphous crystalline, they are solid. They are solid. Okay, look at this. You still remember? Remember, you know, all these are different crystals. Different crystals. So you have a cubic, tetrahedral, orthorhombic. So these are the basic crystals. So usually when you talk about crystalline form, so these are the seven forms. Then remember what's happening, right? Crystalline is you look inside, right? Let's say I look at you, whatever I can see is heavy. Your outer surface, alright? Whatever I can't see is what is inside. So inside actually refers to the different pieces. So different pieces usually refers to what is inside. So heavy is what is outside, what you can see. So if you have something like this, so if you talk about the flow, this will be better, right? As compared to this, right? Why you need to study the different crystal line form and also the crystal habit? Because this kind of shape can affect the flow of the powder. Alright? Alright? So you get something like this, as compared to base, of course, this one will have a better flow. This one I don't think I need to go through. You have done everything in your second year. You know what's polymorphism, right? You know okay. So polymorphism, that is a single drug appears in different polymorphs. Alright, this one is can go on your phone. Okay, you still remember what is the meaning of metastable, right? You still remember? Metastable is something in between, not stable. Because for metastable, eventually it will be converted to the stable form. Then polymorph, you have many polymorph, only one is stable. The rest eventually will end up in one form. Then I hope you still remember the monotropic and inotropic. Okay. Well, I don't know what you don't know. So I tell you know, then you know. So a metastable form may exhibit sufficient chemical and physical stability under shelf conditions to justify its use for vision or pattern disorder or ease of gravity. You understand this, Metastable, although it's not stable, but if this particular compound or crystalline form can last up to 3 years or up to 2 years, you still can use it. Why? Because metastable form will have a better solution and also better solidity. As simple as that. It means certain drugs, although it's in amorphous form, we still can use as long as that particular form is stable throughout the shelf life. Understand? Remember that the difference between amorphous and crystalline, right? Amorphous will have a better solution, solidity, right? Lower melting point, right? Right? Okay, I show you an example. You heard of this atorvastatin, right? Statin. Amorphous is more potent. So all those generic in the market, they are amorphous form. The one original is crystalline form. You cannot touch the crystalline because it's underrated. So a lot of generic companies, they go for this amorphous. Why generic companies still can go for amorphous? Because amorphous can also last for 3 years. But in terms of viability, amorphous will be higher, right? solubility, better dissolution. What do you get? Higher extent of absorption, right? Correct? Okay, I show you another example. I don't know whether you've heard of it. Drug called clopidogrel. It's popular thing. The brand is very expensive. This one also two forms. One form is patented, one form is not patented. So the one generic form is the one not patented. So you can look at the description is the same. You look at it, no difference. White to cream color powder, white to cream color powder. Alright? But if you look at the spectrum, IR, you know what's IR, right? Infrared, X-ray, diffraction, this one you know, right? And DSC. These are the three instruments that allows you to differentiate the different crystalline form and amorphous and crystalline form. You have done this, right? These three you have studied, right? In your secondary, right? How we use DSC, how we use X-ray diffraction. This one is a powder. You have single crystal X-ray diffraction. You also have powder X-ray diffraction. Okay? So you look at this, you find that in the infraspectrum, wavelength, wave number is not wavelength. The wave number is different. You see that? It's 2, 1, 1, 4, 1, 2, 1, 7. And you look at the X-ray diffraction pattern, you see the 2 theta value also different. Then you look at DSC, this one is 177. Alright, this is 184. So by looking at the melting point, basically you can differentiate the different types of this item. So basically this one polymorph, this another polymorph. Okay, understand? Right? So you cannot remember, maybe you can refer back to your second year lectures. Or if you don't want to refer, then you can go to Google. But Google plenty of information nowadays. Eventually you don't need lecturers anymore. Serious. A lot of information you can read. The only problem is whether after reading you can understand. That is only the issue, right? So you can be a lawyer, you can be an engineer, you can be anybody here. Just refer to Google. Plenty of information. But the only difference is you can read, but whether you can understand. That's the separate issue. If everybody read can understand, you are multi-talented. Alright, polymorphic transformation can occur during grinding. You know what's grinding, right? If your powder is big, the cost very cost. You want to grind it into a smaller particle size. That process is called grinding process. You can use another name called convolution. You make it more minute. Alright? Granulating is granulation. Granulating process is actually to convert powder to granules. That's why we call it granulation. You are granulating. Drying, you know, either put into oven or you put into pre-gas drying. Then compressing, compress, WD machine. So these are some of the drugs, vancomycin, spironolactone, and astragalol, are reported to undergo polymorphic transformation. So some of these processes, after going through, you find that some of the drugs, they can change you. Understand? So this process called combination. Combination is this process. Okay, Then you look at this drug, phenylbutazone, undergoes polymorphic transformation as a result of gliding and compression. So it depends on the drugs. Alright? You know what solvent formation? Understand that? Understand that? Wet relation, you can use a solvent. A lot of times you use water. But if the drug or if the compound is easily hydrolyzed, for example, use vitamin C. Some drugs like these penicillin group, they are very easily hydrolyzed when you use water. So what do you do? If you want to go over wet relation, use IPA. You know what's IPA, right? Isopropanol. You have methanol, ethanol, and propanol, right? Yeah, you can use propanol to do the granulation. So a lot of vitamin C, vitamin A, if you can't use in water, you can go for IPA. So when granulation, if you use water, then you can lead to a water, it will hydrate. Alright? With other solvents, you can call it as solvent formation. You know what's called polymer, you know what's pseudo polymer, right? What's the difference polymer compared to pseudo polymer? It's only the water molecule, right? Or the solvent molecule, right? Oh? Yes? Alright, so these are instruments. If you want to look at the crystalline form, the solid state, you can go for this. Just in case you have forgotten, alright? This one is your X-ray diffraction. Alright, these are powder X-ray diffraction. So how we do it? We prepare a powder bed into a sample holder, put into the machine. Then you shine the X-ray, eventually you get something like this. So different polymorph give you different point. Alright? If you compare polymorph, the crystalline form and amorphous, one will give you a boiling point, one will give you a glass transition temperature. Correct? No. So these are melting point. Okay? This one is glass transition temperature. Right? This one is a crystallization temperature, correct? So for amorphous, you keep providing energy. So what happens? The process will be endothermic. That's why you see the big. This is a process of endothermic. It take up energy. Alright? Then amorphous will start to rearrange. The atom and molecule will rearrange. Then you get the temperature. That is exothermic. So you start to have rearrangement. You have to rearrangement everything. So eventually what you get a conversion from amorphous to crystalline. Alright? So you keep heating, what happens? The crystalline form will start to melt. Then you get a melting point. So this melting point is also the endothermic process. So these two Tg and Ti both are endothermic process. Alright? The rearrangement, this one is exothermic. Alright, understand? Okay, we look at DSC. Something like this. This one is for you to compare. This one I give you the example with indopotassium. The alpha and beta. Then over here they have a glass transition. Okay, Okay, we look at this X-ray. This is a two theta value. How do you know where they are crystalline or amorphous? We look at the pattern. You get a halo pattern, then it's amorphous. You get something like this. This one you call it halo. You get something like this, you have a lot of peaks. Then this is crystalline. You have more peaks, that means the percentage of crystalline is even higher. Alright, so every single crystal or different crystals you will have a different pattern of the peaks. Then based on this, you basically can modify the machine, the software will calculate everything for you. But let's see some ideas, you know what to differentiate. So what are instruments that you can go for? So at least you have some ideas. Alright, so we have completed on the characterization on the solid state. Now we move on to the solution. So solution properties, firstly you need to know is the solubility. You know what solubility, right? At certain temperature, the amount that goes into water. Right? So from solid, it will dissolve. Eventually, you will see the solid anymore. Okay? So that's called solubility. Dissolution is how fast. Dissolution always cover the rate. How fast the drop dissolve, go into water. Okay? One is amount, one is rate. So if you want to quantify solubility, okay, before we talk about that, you look at this. This value is a guide. So as a rule of thumb, we call it rule of thumb, compounds with aqueous solubility higher than 1% weight volume are not expected to present dissolution problem. So if you develop a new compound and the compound you found that the solubility is more than 1% weight volume. You know what is 1% weight volume, right? What can I mean? 100 ml. You understand, right? Okay, look at this classification. This is BECS classification. This guy took 10 years or 15 years to cover this. And this is adopted by FDA. And then subsequently, everybody is following. So you have class 1, class 2, class 3, and class 1. Right? If your compound falls under here, no issue. Because high solubility, high permeability. Right? The problem starts to arise if your compound falls in 2 or 4. 2 is low solubility. 4, both is low. Understand? Huh? Number 3 is high solubility and low permeability. So you find that in Malaysia, if the compound falls in class 2 and class 4, it's compulsory to do B, bipolar study. Alright? 1 and 3 is dependent on the type of drug and also the dose. Okay, allopurinol, class 1. You know what's allopurinol, right? The one used for treat uric acid. 100 mg and 300 mg. 100 mg you can get biowaiver. You don't have to do B. Alright? But in 300 mg, although it's under class 1, you still have to do it. Why? Because of permeability. You have done this BCS classification, right? You know what are the criteria, right? The 3 criteria, right? Okay. Now, since it's not okay, so I don't think I need to elaborate. So this, I show you this one. These are the methods that you can improve the solubility. You see that here they go for formulation design. Here they go for link optimization. Link optimization you can convert to the short form. Formulation, you can play around with your formulation to improve the solution or even to improve the solubility. So these are some of the examples. If you're interested, you can look at it. Then you can also go to Google. You go and look up. You just type in biowaiver for BCS. Then it will come up. Everything is there. I also took from Google this one. Not my own. You know, my age, for me to develop all these colors, it takes me many days. So BCS class 1, simple solid oral dosage form. No issue, right? No dissolution problem, no solubility. So you can make into a simple solid oral dosage form. Alright? The second one, class 2, you need the techniques to increase surface area like particle size. This one basically to increase the solution. Remember, we talk about particle size reduction, we talk about solid solution, we talk about solid dispersion. Then solutions using solvents and or surfactants. This one, what's the purpose? Increase the permeability. So solvents you can go for solvents, alright? Number 3, incorporate permeability enhancer. You know what's permeability enhancer, right? That can improve the permeation. Then number 4, you have to combine 2 and 3 together. Because BCS class 4, both also low solubility and low permeability. Okay, how do you determine solubility? The simplest form is you take a beaker inside your 100 ml of water, slowly add until the stage you start to see saturation. You know what saturation, right? You know non-sink condition, right? That means you add until you start to see solid. That means that's the stage the compound is not soluble anymore. Right? Then you stop. You record the amount. You know the volume of water, you know the amount that added. So you will give you the value, right? Okay, this is more difficult. This is quantitative determination. You add until the solution is saturated. So you get a saturated solution. Then you shake. Alright? So prepare a suspension of solid. Suspension. That means not dissolved. It's a non-sink condition, right? Saturation. Or we call it saturated solution. And shaken at constant temperature. So what you do is you prepare a bigger, not bigger flask. 100 ml, you add it until saturation. Then you put inside a water bath shaker. You know what's water bath, right? Water bath? So temperature, so you set maybe at 37. Then this kind of water bath, it has a shaking mechanism. So you put in the needle, on the rotation per minute. Now you set yourself how many shake per minute. Rotation or rotation. You shake like this, right? Then you just leave that. So samples be drawn periodically and treated. You collect sample, let's say for example, I leave it there, water bath shaking for 5 days. Day number 1, after 12 hours, I collect. After 24 hours, I collect. The next day, I collect 1. So how many readings? Did you collect until 15? 6 readings, right? Right? So from this 6 readings, after sample I collected, I spin centrifuge. Why I need to centrifuge? I want to precipitate the drug that is not soluble, correct? I collect the supernatant. You know my supernatant, right? The top layer, the clear layer. Then I filter again. I go through a stage filter. So now I get a clear solution, right? Then what you do next? You either go for UV spectrophotometer or you go for HPLC, right? You construct a standard curve, then you inject a sample. So from there, you can quantify, right? You know your standard curve, you know the unknown sample, you go in. If you use HPLC, you look at the type of area, then you know concentration, then from there, you can estimate what's the concentration. If you use UV spectrophotometer, you base on the absorbance, right? Now you have the standard curve, you have the concentration absorbance. So from there, you can also calculate. So you will estimate until a saturation point. You know a saturation point, right? It goes up, then it becomes plateau. So this one, it goes something there. Something like this. Yes, it goes up, then it stays. So this is called steady state or saturation or we call it plateau. That means go up, it doesn't change anymore, no? So that point, you can take it as your solubility. Understand that? Very simple. Okay, pH solubility profile. If your drug is acidic or basic, you have to do this. What you do is, you can go for pH 1.2, 4, 4.5, 6 or 6.5, 6.8. You can take one more reading, at least 9. Or if you want one more, you can go for 12. So different pH, you check the solubility. Then from there, you can draw a graph. Understand? You can draw solubility against the pH value. You need to know, especially if your drug is acidic or basic, at least you know the property of your compound. At certain pH, what is the solubility like? Okay, you have come across this term, right? Common ion effect. Have you been exposed to this term? No. Alright. You look at this solubility product. Your gastric is under acid pH, right? Correct? 1.2 to 3. After food, maybe 4 to 4.5. But it's still in acidic condition. So assuming if you take a drug, this drug is acidic. So what happens to acidic drug if you put this acidic drug into an acidic environment? What happens? Solubilize? No. Correct? Acidic compound in acidic pH is in unionized form. Correct? Correct? This is called common ion effect. Understand? Gastric contents are high in Ca, Cl minus. Alright? The common ion effect phenomenon suggests that one should use salts other than HCl to benefit fully from the enhanced solubility due to a salt form. If unionized form, what happens? Not soluble, right? Correct or not? Correct, Yes. So they suggest you should go for salt, but not the HCl. So what else you can have? Nitrate, sulfate, right? But in actual practice, in clinical, this is not true. In theory, this is true, but in actual fact, it's not true. Why? Because the absorption is not in the gastric, right? Right? We have studied physiology, right? The absorption is in the small intestine. But you need to know the common, what is called common effect. That's why, despite this, many drugs are used as HCl salt. Because solubility of most HCl salt in the presence of Cl, ion, oxygen, bromine, and carbon are sufficiently high. Alright? So suppression of solubility due to common ion effect under these conditions is not of sufficient magnitude to affect the solution or viability of this compound. Understand? Okay, you understand what's happening in solubilization, right? You have studied the surfactant. You have studied surfactants, the effect of surfactant on the solubilization. Right? Okay, look at this. When the drug substance under consideration is not acidic or basic compound, or when the acidic or basic character of the compound is not enable to the formation of a stable salt, other means of enhancing solubility may be explored. You understand this? So how can I do it? Use of a more soluble metastable polymer. Remember, just now we talked about metastable? Alright, metastable form will have a higher dissolution and solubility. You can go for complexation. Alright, so later I will show you one of the methods, complexation method, that can improve the solubility. Then you can also go for cold precipitation. So how do you do it? You combine with a hydrophobic compound. For example, glycophorin, they use PG. So you melt both together, eventually forms we call it cold precipitate. So this cold precipitate basically consists of the drug plus the polymer. So eventually, instead of a single component, you get two components. So that is called cold precipitate. So the process you can call it as cold precipitation. Occasionally, a less soluble form is desired. Not all the time. Not all the time you go for the higher soluble type. So how do you know when you should go for this, when you should go for that? You should capture all this information during your clinical study. Understand what I mean? That's the reason why during clinical study, phase 1, phase 2, phase 3, you have to look out for all these possibilities. Alright, and this is the conclusion. That's why those studies, after you get the data, how to analyze, how to deduce the conclusion, that is very important. A lot of times you run, like I look at you run practical, I doubt you know what you are doing, right? Right? Eventually what you're supposed to do, or what is your expectation? A lot of them, I don't say you, I say a lot of them. A lot of them, they do it blindly, so at the end, they also don't know what they are doing. So by right, when you do something, you should know what is your final objective. Alright, coming back to here, clindamycin, a less soluble palmoate salt. Clindamycin, you can get a base, which is clindamycin. You can also buy the salt form. The salt form is actually a palmoate, clindamycin palmoate. It's preferred over the soluble hydrochloride hydrate to circumvent the problem of the unpleasant taste. Same thing also, chlorphenicol palmitate and chlorphenicol. Remember? When the drug is deactivated by the acidity of calcium fluid, the less soluble form is also preferred. This is what another one. Oh, why suddenly so many want to pee? You want to pee, right? Right? Okay, you know what's called case hardening? The use of solvent with a high capacity to dissolve the active ingredient can lead to a phenomenon known as case hardening. Understand this one? If a drug, right, if I put granulation, if the drug is highly soluble and the proportion of the drug in the tablet is very high, you have to be very careful. You put a little bit of water, everything becomes wet. Right? So wet then you got the lump. So for this kind of situation, you have to really pay attention. So solute migrates and deposits on the periphery of granule during the dry operation. Understand anyone? Okay, I think the solution you have done also right in your second year. Okay, so I hope you still remember what is Ka, what is Kd. And what is the rate limiting step? Right? The step slowest, right? The step that is the slowest will be the step that will determine the dissolution, right? So you look at the absorption rate and you look at dissolution rate, right? So in this one, is very large compared to this. So what will happen? Okay, this one I don't think I need to. Alright, let us look at parameters affecting the absorption. Three parameters have to characterize the formation. Remember just now BCS classification? You talk about solubility, you talk about permeability, right? Okay, look at this. Three parameters help to characterize the permeation behavior of a drug. One is solubility and dissolution rate, this one we know. The second one is partition coefficient. I'm not sure whether you have gone through this partition coefficient. Anyway, I show the picture later. The last one is in vitro transport measurements using molecular membrane. This is actually a set of experiment. You can use, I don't know whether you've seen the device. One is like something like pencil. Alright, you have top part, you have bottom part. That is called vertical type. The other one is horizontal type. You put the membrane in between. You have two compartments. One compartment they call it donor cell, one they call it receptor. So donor and receptor chamber. Frank cell on top is donor, below is receptor. Alright? The membrane you put in between. You put the drug at one side, you collect sample from the other side. So if the drug permeates through, then when you collect from the receiver or the receptor chamber, you should be able to detect the drug. Alright? So this one you understand? Okay, let us look at the partition coefficient. Partition coefficient is important because in future, when you look at log P value, you will understand what is actually log P. Okay, you look at this. This is called partition coefficient. Then you can calculate. I show you this picture because quite creative. You see, they use the 4 dot, that's the 2, 4. Right? 1, 2, 3, 4. Right? Until the calculate is 1. Over here, they have 12, then they have 36. Then they show you how they calculate. So basically, partition coefficient, you need two different solvents. And these two solvents are not supposed to be visible. Then you quantify the drop in the aqueous layer. You have no way to quantify in the organic layer. You can only quantify in the aqueous layer. You know the amount of drug you put in, you know the volume, right? So you collect, you know the volume in the aqueous, then you know how much is distributed into the non-aqueous layer. Okay, So in the lab, very simple. You can go for this kind of what do you call this? Separation partner, right? You got separation partner, right? So you put in, then you just shake, right? So after shaking, then you leave it there, then you start to collect the aqueous layer. So when you shake, don't shake too much. Because once emulsion is formed, then you have to repeat the experiment. So you look at log value. So log P is actually how you calculate. Alright? Understand? So log P will give you the partition coefficient. Okay, for ionization constant, this is more to the chemistry part. Factors that are important in the absorption of weakly acidic and basic compounds are pH and the site absorption. Remember, just like I mentioned to you, it's your microenvironment. Your ionization constant, right? And your likely solubility of the unionized mixture. Okay, Okay, these two equations you have to remember for life. Anderson has about equations. Why? Only at looking at this, once you know the pKa, you know the pH of the environment, then you know what is the ionized and unionized form. Okay, Yeah, remember? This is called Frank cell. This one, it will develop the transdermal dosage form. You know transdermal? The one like oil. But oil is for local effect. Transdermal is for systemic. You basically the drug is supposed to go through your cerebral and into the bloodstream. So that one is for systemic effect. So what you have nicotine patch, you have those ketoprofen patch, those actually for pain, and also for morphine. Those cancer patients, we also have patch that carries the opiate. So this one you can see, if you want to see, you go to the lab. I think there's one you need. This is actually the prime stuff. Alright, any questions so far? Okay, okay, move on. This is stability. Okay, I want to expose you to this term called stability indicating HPLC method. This method, after you have developed, it should be able to pick up if there is degradation. Alright? So let's say I compound. Remember just now we talked about impurities or those related substances. Right? And remember I told you related substance you have to qualify. So after you have bought the API, you are given the COA, right? So once the raw material or once the API reaches your factory, QC has to take the sample. Okay? After taking the sample, you have to create your own COA. You follow the COA supplied to you. You start to repeat some of the parameters. You come up with your own COA. And this COA you have to submit when you register your products. So some of these parameters you need to know. So when you want to quantify, after you have developed the tablet, you put into stability channel. Then you monitor real time and accelerated. Okay? So in Malaysia, usually you can do for accelerated, you keep at 40 or you can keep a higher temperature. Alright? So usually 40, 75, you can keep for 3 months. Then they will allow you to register for 2 years. If you keep for 6 months, they will allow you to register for 3 years. Alright? So what you do is, when you put into accelerated stability, on and off, you have to take out a sample to assay. So when you assay, you have to assay for the drug, the active, and also the related substance. So if there is degradation, you want to know the degradation, right? The original compound, you start to pick up. Then you start to have those impurities or those related substances. So your method that you have developed must be able to pick up. That means I must be able to detect whatever degradation products you have in the product. Understand? So that is called stability indicating. So when you develop stability indicator method, how did you do it? You have to go through certain process. Alright? You have to use H2O2, HCl, and OH. So there are certain parameters that you have to do it. This I know who is teaching HPLC here. So that the person will teach you how to do it. Right? Okay. For solid state stability, you have heat, light, oxygen, and moisture. In Malaysia, or ICH guideline or ASEAN guideline on stability. So in future, if you work in factories, I know most of you don't work in factories, because pharmacists get to work in factories. No, serious. For the last 30, 40 years, I think less than 10. Not less than 10, maybe less than 15. I think less than 10. Those graduates from USM will end up in industry. Most of you are in clinical hospitals or in retail. Alright, but at least you get some ideas, alright? So you have keep, usually when you run stability, you have keep because you keep at 30 degrees Celsius and also 40. Alright, these two are compulsory. Because Malaysia is fall under zone 4B. Right? So you find that a lot of products you bring import. Eventually, if let's say you are the traders or you are the distributors, you bring products from Europe, you find that their stability, they don't do for 40, 75. Because their countries do not fall in our zone. So our zone is zone 4B. Alright, so zone 4B, you have to follow two temperature, alright, 30 and 40. Then 30, 40, also you have to follow the 75% relative humidity. So you have the effect of heat, you also have the effect of moisture. Alright? So light and oxygen is dependent on the compound. The compound like omeprazole, compound like ketoconazole, they are light sensitive. You have to think of a way to protect the product. So what you do is, you can pack into alu-alu. You know what's alu-alu, right? Packing. Am I? Don't know. Anyway, I'm teaching you packing. Okay, I will come to that. Or you can go for a container that can build out the life. That oxidant, not many products, but they are. Have you heard of retinate? You heard of one retinate or this retinol acid? That one is very sensitive oxygen. So when you pack, they blow nitrogen. If you are rich, you go other, then only after that, they start to pack. Other packing, they blow again. So the Higgs space, you know what's Higgs space, right? Higgs space is also filled in the gas. So a lot of time in the gas we use nitrogen because nitrogen is cheap. Argon is more expensive. Alright, so under stability, there is a condition called stress condition. Stress condition is also the same as accelerated stability. You put the product under stress. That's why we call it as stress condition. Why stress? You want to register the product. If I want my product, I claim that the product can last for 3 years. It won't spoil, it can last for 3 years. You need to prove, correct? So I can't wait. After 3 years, I'll register, I go and can sell, right? So what I do is, I will create a stress condition. So this stress condition is part under accelerated stability study. Don't worry, all my will cover. But at least you know, you get some ideas. Many words those words you can go through, but I explain to you, at least you get some ideas. So this is called elevated temperature studies. I think that practical you will be exposed to this, correct? So elevated temperature studies, you go for higher temperature. Let's say I started with 30. 30 you assume is room temperature. 30, 40, 50, 60, 70, 80. Okay? So elevated temperature, you can go to 60, go to 70, go to 80. So what happened is, I put the tablet into the oven at different temperature. Okay? After some time, I take it out. I check the content. So at this particular temperature, I have a value. So if I use 5 different temperatures, I have 5 different values, right? So from there, more or less, I can tell at this temperature, the drug has degraded this much, at this degraded this much. Then from there, you can start to draw a line. Okay? Alright, so at least you get some ideas. Don't worry, if you don't know this, later when you study stability, you will be exposed to this. Alright, so the other time is called real-time stability. Real-time stability is a must. Accelerated stability is allowed to register products. So as you move on, you have to collect a reading. So what you do is you collect 3 months, 6 months, 9 months, 1 year. After that, the second year, you collect every half year. The third year, you collect 1. So if you want a product to last for 5 years, you have to carry on the 4th year and the 5th year. Understand that? So you collect the 4th year, then you write into MBRA. You ask MBRA to extend your shelf life. So for subsequent batches, you can put 4 years. So by the 5th year, if you are able to show that your product is still stable, with stability data, you submit MBRA. Then you ask for extension again to 5th year. So those subsequent batches that you prepare, you can claim the shelf life up to 5 years. That's why you see some of the products in the market, some can last for 4 years. Correct? All imported products, MPRA allows only 2 years. If you want to have 3 years, you have to run stability in the country. Correct? With the data, then you claim for 3 years. Then you claim for 4 years. But if the local manufacturers, you can register straight away for 3 years. Alright? For 4th year, 5th year, then you can apply. Every country is the same. You will protect your own industry. It's how expensive or how far you will protect your own industry. So stability under humidity, same. Different humidity, same like you have done in your practical. Right? You can use different salts. If you don't have money, because you want to buy humidity, you have to buy many humidity. Alright? So if you don't have money, you can use the salts to create the kind of ready humidity. The different salts will give you different ready humidity. Then you put the product inside. After some time, you collect, then you assay. When every time I talk about assay, you understand what is assay, right? ASSAY, not ESSAY. Assay, ASSAY. Assay means you check the content. Okay, no. Those days, after I completed all my lectures, 10 hours lectures, the student come to me and ask me what is essay. You understand or not? Okay, the photolytic stability, this is actually light sensitive. Alright? So light sensitive, you can buy those commercially available, those lamp. This lamp you can go for 400 or 900 foot candles. This actually unique for the intensity of the light. Alright? Like this one is called fluorescent, right? So that kind you can buy. So same thing, you put your product, you expose to the light over a time period, then after that, you quantify, you assay for that. Then see whether it's stable. So every time we run this experiment is in your final form. Not the tablet exposed like this, it's already in your final packing. If okay, then it's okay. If not okay, you have to change your final packing. Understand? Not expose your tablet like this. Okay, this one is stability to oxidation, right? If your compound is easily oxidized, how you want to do it So sensitivity to oxidation can be extended by investigating stability in an atmosphere of high oxygen tension. Usually a 40% oxygen atmosphere allows for a rapid evaluation, right? So these are some of the conditions that you can go for. So not necessarily you must follow 40. This is actually a suggestion. You can go for 45, up to you. Even the elevated temperature, it's up to you the temperature that you want to decide. Okay, drug excipient compatibility. Remember, I mentioned to you, you make tablet, not only the drug itself, right? You have other components. You make the capsule, it's also the same. You make cream, you make ointment. Okay? So cream, you have aqueous phase, you have what? Phase, right? So you have all those components. So those components, as long as they are not active, then we call them as excipients. So excipients, you have to make sure that there's no interaction between the excipients and your drug. You see, in the US, if you are a generic company, so every time when you develop a formulation, you have to follow exactly the type of excipients used in the original product. Different from Malaysia. Malaysia, you can develop a generic. The components of excipients can be different. You got it? So it depends on the country that you export to. Certain countries you want to export to. So when we develop the products, we always refer to summary of product characteristics of the original product. So under the summary of product characteristics, you can find excipients. A lot of times, because they have to report. Patent, right? When they file for patent, we have to declare everything. So for us, as a formulator, we always refer to all these. We call it as literature. Like you are doing research, you always refer to articles, right? The publications. But in industry, you want to find a patent, you can call up a patent lawyer, do a search, or you can go to Google. Because some of the websites, you can get research. It's free of charge. Then read the patent. And also, summary of product characteristics is also a must. Or this precedent test. So all these you can get this info. So also status are problem. Even those excipients, you know that there's no interaction. Otherwise, it won't appear in the original product. So if you want to go for your own excipients, try to look for those excipients that are in MCC, lactose. Don't go for those compounds or those bacteria that are not common. Understand? Because generic, the generic companies, you try to develop the product as fast as possible, as minimum R&D as possible. So these are some of the techniques, chromatographic techniques you are using either HPLC or TLC. If you go for traditional, then of course you can go for TLC, thin layer chromatography. But nowadays, thin layer chromatography is not sufficient because at the advance of technology, a lot of herbs now basically you can sanitize. You know what is the seed inside. Then a lot of times they ask you to sanitize. So like for example in Pokali, they will ask you what is contaminated with or not. You talk about this, I think many Chico, they will ask you Chico like what is the content. So HPLC you can't run away. I foresee another 5 to 10 years, most of the industry has to go for LCMS. And because the price of LCMS also getting cheaper and cheaper. Those days 10 years ago, or 20 years ago, 20 years ago I was like you. Those days you want to get one HPLC also difficult. Now HPLC is so rampant, and the price is so cheaper. Those days are 4-5 times the price. So it will be getting more and more sophisticated. Like those days I never heard of little substance. 10 years ago. Right? I graduated in 1992. What a year. So those days you never heard of. But nowadays you have this little substance in quantities. Then those days, a lot of detection, you go for UV only. Now if you refer to monograph, mostly HPLC method. So slowly, all this you need to be exposed. You have to learn. So DTSC